This is the example on slide 51 of our chapter 20 part 1 PowerPoint. And here they want us to, without looking at the standard cell potential, predict two redox reactions and if they're spontaneous. And if they are spontaneous, they want us to draw an electrochemical cell in which the reaction could occur. So I'm going to show you how to do that. So we're going to start with A, which is iron reacting with magnesium 2+ to produce iron 2 and magnesium. So first things first, we need to figure out what's oxidized and what's reduced. So we're going to assign oxidation states to everything. Iron solid is 0, magnesium 2+ is +2, iron 2+ +2, and magnesium solid 0. So magnesium is undergoing reduction and iron is undergoing oxidation. So then, after we identify that, you're going to consult your table 20.1, which is on slides 41, 42, or 43, to figure out the standard electrode potentials of each half reaction. So for our reduction, magnesium 2+ plus 2 electrons gives you magnesium solid. If you look on your table, the standard electrode potential for that is negative 2.37 volts. And for the oxidation, now be careful when you're looking for this because there are several iron reactions. It's iron, and these are all written as reductions, so it's going to be iron 2+ to iron 0 when you're looking. There's a couple going from iron 3 to iron 2 and going from iron 3 to iron 0, so make sure you find the right value. So for this guy, it's going to be Fe solid, and I'm writing this as an oxidation reaction, but the standard electrode potential is technically for a reduction. Iron going to iron 2+, and that's including 2 electrons. And the standard electrode potential for that is negative 0.45 volts. So now is the part where we determine if it's spontaneous or not. So in order for a reaction to be spontaneous, the more negative of our standard electrode potentials, that half reaction has to undergo oxidation. So in this case, our magnesium half reaction is much more negative than our iron half reaction. But it's not undergoing oxidation. According to this reaction, this overall reaction that we have written, it's actually undergoing reduction. Therefore, this reaction, as written, is not spontaneous. Now, if we reversed the two and had magnesium undergoing oxidation and iron undergoing reduction, then it would be spontaneous. But as it's written now, that is a no. It's not spontaneous. So for our second example, we have iron reacting with lead 2 to form iron 2 and lead solid. So first, we got to figure out what's oxidized, what's reduced, and that goes with determining oxidation states. So iron is 0, lead is +2, iron +2 is +2, and lead solid is 0. So iron is undergoing oxidation this time, and lead is undergoing reduction. And so now we can look up the half reactions of both of these. So lead 2+ to lead 0 is written like this. And if you look up the value, on your standard electrode potential table. For this half reaction, it's negative 0.13 volts. And for iron, Fe forming Fe2 plus 2 electrons, its standard electrode potential is same as previous, negative 0.5 or 0.45, sorry. So remember our rule: to be spontaneous, the more negative electrode potential has to be the half reaction undergoing oxidation. So in this case, our more negative is our 0.45 volts, and this is undergoing oxidation. Therefore, our reaction as written is spontaneous. And there you have it. So the question also states, if the reaction is spontaneous, make a sketch of the electrochemical cell in which the reaction could occur. In your sketches, make sure to label anode, cathode, and direction of electron flow. So this is something we have not done yet, but I'm going to show you how to do just kind of a simple sketch for this. So in any electrochemical cell, you're going to have a beaker where the reduction or oxidation is taking place and vice versa. So you're going to have two beakers, and both of these need to contain some sort of electrode. So I'm drawing that in the form of a solid strip. And these strips are going to be connected by a wire. And then below the wire, that's how electrons are flowing. I'm also going to have, this is your salt bridge to make sure that ions continue to flow. So the convention for these, the oxidation is always written on the left-hand side. Reduction is always written on the right-hand side. And in case you are not familiar, oxidation occurs at the anode and reduction occurs at the cathode. And a mnemonic to help you remember that: red cat. Reduction, cathode. Oxidation, anode. So, our oxidation half reaction is iron solid going to iron 2+. So my electrode, which is that solid strip I have driven here, is going to consist of my iron solid, because it is a solid and it's a metal that conducts electricity. And in solution, we'll draw a little line for indicating solution, I'm going to have my, and these are standard conditions, so we'll say 1 molar iron 2+ solution. On the other side, my electrode is made up of, I have lead solid and lead 2+. My electrode's going to be made up of my lead solid, and my solution is going to be 1 molar Pb 2+. So now what I need to do is indicate what's the anode, what's the cathode, and where electrons are flowing, in what direction they're flowing. So anode has oxidation occurring, so this little strip with the iron is the anode, and it is negatively charged. That's the convention for anode, and that is written on a slide previous. Let's see if I can find it here. Slide 29, electrodes and salt bridge, indicating conventions. So that means the lead strip is our cathode, and it's indicated positive. Now, since something's being oxidized, remember the things that is being oxidized is basically donating its electrons to the thing that's reduced. So therefore, my electrons are flowing from the anode to the cathode in the right direction, literally left to right. So typically we indicate that, if you're following along on your slides, with just a little arrow saying that's the way electrons are flowing. So there you have it. That's a very crude drawing of a electrochemical cell, but that's how you would go about drawing one.